Okay, this is the slide from the end last time. We didn't quite finish it. Equilibrium versus resonance. Remember, equilibrium is a case where you have two different species, different structures, and you go back and forth between them, maybe fast, maybe slow, okay? Like the hydrogen could be attached to the top, or it could be attached to the bottom oxygen, and those are different, two different, what's called isomers. We'll get to that later on. Or you could imagine the same thing. If you take the hydrogen off, you could have a short double bond to oxygen and a long single bond to oxygen, or they could exchange as to which oxygen was long and which was short. So you could have an equilibrium there, but it turns out you don't, right? That in fact it's not two different species, right? It's one species. It's a single minimum, not a double minimum, right? Now, how do you know this? How do you know it's just one nuclear geometry with an intermediate bond distance? The only way you know is by experiment or by some really fancy calculation that you have to believe. A lot of people would believe experiments before calculations. Some are the other way around, okay? But there's evidence from a technique called electron paramagnetic resonance, or EPR, that shows that indeed this is one species, a single minimum, right? Or if you have an extra electron on it and you have the carboxylate anion, then again, it's just one species, a single minimum, right? And there's evidence from that from infrared spectroscopy that we'll talk about next semester. Okay, but don't be disappointed that you're not able to predict this. A lot of really smart, experienced people couldn't predict it, right? This is lore. If you look it up in the Oxford English Dictionary, it says that lore is that which is learned, learning, scholarship, erudition. Also in recent use, applied to the body of traditional facts, anecdotes, or beliefs relating to some particular subject. So a lot of things are lore. You just have to learn them, right? You can't predict them ahead of time. They're way too subtle, right? So don't be disappointed because you haven't had enough time yet to get the lore. You're not supposed to know it yet, right? It would be nice if Lewis theory was so accurate and straightforward that if you draw two structures, there are two structures, and it's a double minimum, right? But that's not true, right? And you have to know from something, and you don't have time to know yet. As time goes on, maybe you'll figure it out. This is from a good textbook. It might be the one that we'll adopt next semester. It's a quote that says, empirical rules, it's going to give empirical rules for assessing the relative importance of the resonance structures of molecules and ions. That is, if you have two different pictures that you can draw for the thing, does it look halfway in between them, almost all like one, almost all like the other, or some fraction of the way between them? How far is it one way or the other, right? These are two different pictures you draw to try to show different aspects of the same thing. But there is one real thing. The molecule doesn't know about resonance, right? It just knows what it is. The problem is with our notation. Okay, but anyhow, here's what they say. So rules that will allow you to use this concept more productively by deciding which ones are better, which look more like the real thing. Okay, so it gives rules and it numbers them. 1, resonance structures involve no change in the positions of nuclei, only electron distribution is involved. That is, when you draw these two structures, you don't move the atoms. You just change where you draw a single bond or a double bond or a dotted bond or something like that, right? And in fact, that's not even true because it's not, the electrons know where they want to be, right? It's the way we draw them that's uncertain, right? So when you draw two different resonance structures, you're not changing where the electrons are, you're just changing the lines you draw. Is that clear? It's our notation that's at fault. Okay, number 2, structures in which all first row atoms have filled octets are generally important. However, resulting formal charges, we talked last time about how you get formal charges, right? And electronegativity differences, and of course we have to know what electronegativity is, but you've heard about it at least, can make appropriate non-octet structures comparably important. If you have a bad charge distribution, even though you have octets, it still might not be a very